Few days to go through this. When we start this tomorrow or the next day when we start up with the next section, when you go to quizzes where you put in the code, you're not going to have to put in the code again. Right underneath it, you'll see a section that says recent activity. You click on that and it puts you right back in where we were. Okay, so you don't have to worry about putting the session. Just every so often we'll have to kind of refresh it. So we'll be able to kind of pick up where we left off each day as we go through. All right. Again, like I said, a lot of this stuff hopefully you've seen before. Some of it will be new. If you don't understand something, I'm going to slow you down so that you can get the help that you need. All right. We're going to start with real numbers and algebraic expressions today. We should be able to get through all of 1.2. We'll spend 2 days on 1.3 and 2 days on 1.4. Section 1 is just like an intro section of tools for success in math. There's no actual math in it, so we don't jump right into section 2. Okay. So algebraic expressions and real numbers. So to start, okay, algebraic expressions is just a combination of numbers and letters, okay, with operations, plus, minus, multiplication, square roots, cube roots. All of the different stuff that we can do, all the different operations that we can do with a combination of numbers and letters. The letters, we're called variables, can represent anything. Okay? Depending on the situation, we'll be told what they mean. We may have to find what they are. They may be a bunch of different things. All right? Expressions can be as complex or as simple as we want. The simplest expression would just be a number or a letter. The simplest that we could get would be x. That's an expression. 7. That's an expression. We can start adding in operations. 3x plus 5. And we can get more and more complicated as much or as little as we want with our expression. Something I like to differentiate really early on is if anyone can tell me what is the difference between an equation and an expression. Close. There's a little bit bigger distinction, but you're on the right track. With that equal sign, it allows us to do some solving and evaluating. Okay, so an equation has an equal sign. It's right there in the word equation. Expression does not have an equal sign in it. But it doesn't mean we can't solve. Because what we can do is we can define what those variables are. Okay, we can the variables, and then we can what we call simplify the expression or evaluate the expression as long as we know what the variables are. So I have the expression of 5x minus 2y. It is not an equation. So on its own, if we ignore everything else, I can't solve it because I don't know what x is, I don't know what y is. But we can add on to it and say, well, what if x equals 8 and y equals 2? Okay, what am I going to do with this 8 and this 2 in order to evaluate?
Fill x in for y would be 5 times.
Good. We're going to substitute those variables for the numbers, and then we're going to perform the operation. So we have 5 times 8 and 2 times 2. Okay, so I want you to go ahead and on your screen, you're going to fill in. Okay, if the game doesn't load or if the quizzes ever gets hung up, and what you see on my screen you don't see on yours, just refresh it, and it should. So you're going to type in, if we have 5x minus 2y, and x equals 8, and y equals 2, what does it evaluate or simplify to? Just type in your answer. All right, so we end up getting 36. 5 times 8 gives me 40. 2 times 2 gives me 4. 40 minus 4 gives me 36. Evaluate it. Okay, questions, comments, concerns, queries? All right, now let's talk about sets of numbers. So we're going to start off with what I like to call kind of our basic sets of numbers, and we're going to start with the natural numbers. The natural numbers are often called our counting numbers. Why do you think they're called counting numbers? Yeah, we learned math, we learned to count, right? Okay, my son's homework was to count to 5, so he had to go 1, 2, 3, 4, 5. Okay, so it's our counting numbers. Is what we start with. They're the natural ones. They're just kind of part of the natural world. I have 1, 2, 3, 4, 5 desks. I have 1, 2, 3, 4 students. Okay, they're our counting numbers. This is our set notation. This says, okay, this is a set of numbers that's going to follow this pattern where I count by 1, 2, 3, 4, and that ellipse means that we're going to keep going. And we're going to include all the numbers after that that still follow that pattern. So if I think of a larger number, say 10, is 10 part of the set of natural numbers? Yeah, because it's included and follows that pattern. Is 10.5 part of the natural numbers? No, because it doesn't follow that pattern. Okay? It doesn't follow that pattern of counting by 1 over and over and over to continue. Okay? Our next set is the whole numbers. What's the difference between whole and counting numbers? Formal definition for our whole numbers is all the counting numbers and 0. Okay, so it says whole numbers is this plus 0. Okay, and we're going to follow that same pattern with integers. Okay, what's the difference between integers and whole numbers? Negative. We have that negative. So integers is all of this plus negative numbers. And we see we have the ellipsis on both ends because we're going to continue towards a positive infinity direction, and we're going to include towards a negative infinity direction. Okay? And now, so we have 10, right? 10 was a natural number. Is 10 also a whole number? Yeah. Is it also an integer? Yeah. If I have negative 1, negative 1's an integer. Is negative 1 also a whole number? No. So when we go down, anything that's in this set doesn't necessarily mean it's going to be a whole or a natural. But if it's in the natural set, it's automatically included in the whole. It's automatically included in the integer because the definition of each set expands on the one before it. Okay? And all of these, and we'll talk more about them in a second, all of these are subsets of our rational numbers. Okay? We'll expand more on rational in a minute, but those are all subsets of our rationals. Rationals include more than just these. We have more, but these are all subsets of our rational numbers. Okay, so let's look at a couple sets. So we're going to start with the number 0. And I want you to tell me which sets is it in. Choose all that apply. What set or sets is 0 in? Okay, is 0 a natural number, a whole number, and or an integer? Which set or sets is 0 in? Natural, whole, and or integer. Okay? Alright, pretty good. It is both whole and integer. Okay? But remember, 0 is not in the natural set. Natural starts at 1, whole starts at 0. On the choose all that apply ones, when you're picking more than one, you have to hit submit. Maybe try and zoom out. You might have to fiddle with it. Alright? Number 7. Number 7. What set or sets is 7 in? What set or sets is 7 in? Natural, whole, and or integers. What is 7? All of them. Okay? Since 7 is in the set of natural, then it's automatically included in whole and integers. Alright? Last one. -5. What set or sets is the number -5? Natural, whole, integers. What set or sets is -5 in? It is only an integer. It's also rational, but it's not whole and it's not natural. Of those 3 sets, it's only in the integers. Because our integers is all of the whole numbers and negative numbers. Okay, so negatives we don't have in the whole, but negatives are in the integers. Okay, Now, those were our basic sets. Now we're looking at some of our more complex sets. So I talked about the rational numbers. The whole numbers, the integers, and the counting numbers are all rational numbers, but we have more than just those. Okay? So our rationals, our formal definition is anything that could be written as a ratio. Ratio is just a fancy word for what? Fraction. Okay? A ratio is just a fancy word for a fraction. Can I write this number as a fraction? Okay? If it can be written as a fraction, we don't have to write it as a fraction, but if it has the ability to be written as a fraction, then it satisfies as a rational number. The only caveat is that we have to make sure that our denominator does not equal 0. What happens if I have a denominator of 0? It's not 0. If I had 5 over 0, what is that? Not irrational. Not imaginary, but even closer. Take 5 and break it up into groups of 0. How many groups do you have? 5 cookies and break them into groups of 0. Nothing, and you still have 5 cookies over and over and over. So dividing by 0 is undefined, which is why we can't have a denominator of 0. So as long as we can make a fraction with integers and there's no denominator of 0, we have a rational number. All right? Now, really simple example, 1/2. Hey, I have a fraction. It's rational. Is 1/2 an integer? Did it follow that pattern that we had for integers? No. We had 1 and 2, but we didn't have 1/2. So it's not an integer, but it is rational. Okay, so it's in that new set of rational numbers. But it's not just fractions. 0.5 is rational because I can rewrite it as a fraction. So therefore, it's rational. Okay? Now, while 4 isn't a fraction, how can I write any whole number as a fraction? Put it over 1. Now it's a fraction. Now I can see why it's rational. It can be written as a fraction of integer numerators and denominators. Okay? So as long as when we simplify or rewrite the expression, if we can get it to fit this rule, then it's rational. And we'll see a lot of different examples with that. Yeah?
So basically, as long as it's not 0, like 0 is
If we can write the numerator and denominator have to be fractions. So let me give you like a really complicated one that it won't work. So say I have the square root of 3. Okay? I can technically write this as a fraction, but is the square root of 3 an integer? No. So it's not rational, it's irrational. Okay? Same thing as if, I had like pi. Okay? I can write it as a fraction, but pi is not an integer, so it's not rational. And since it's not rational, our next set is irrational. And this one is separate. Everything that we've done before has been a subset, starting at rational and going all the way down to our counting numbers. Irrational, its definition is not rational. They say, it's not this. So if it's not this, it's irrational. Okay? And so these numbers are irrational because they're not rational. All right? And I mentioned square root, and we'll see that on the next set. Again, we have to think about the whole simplifying. Can I simplify the number? Because sometimes we have big numbers, and we can make them small. Same thing if I had 4 over 2. Okay? 4 over 2 is rational because it can write it as a ratio. But 4 over 2 simplifies to what? 2. Which means it's also an integer. It's also whole. It's also natural. Okay, so we have to simplify the number to see what are all of the sets that it goes in. And then all of these are sets of real numbers. That's going to be 99% of what we deal with is real numbers. Later in the year, we will be dealing with non-real numbers or our imaginary numbers. But for now, we're going to be focusing on the real numbers. Okay? And real number just means it corresponds to a point on our number line. I have 0, I have 1, I have -1, and or 2 or whatever, and I keep going forever. If it's on that number line, then it's real.
What's an example of a non-real number?
Square root of -1. That is the non-real number. That is the non-real number, and there's variations off of that, but it all comes down to this is our only non-real number. And then everything else is just, right? That'll be quarter 4. So we got some time till we get there. All right, I have to skip a slide because I order. This is my chart. I love this chart. Okay, this chart shows that nesting, those subsets. Okay, so we started at first with our natural numbers all the way at the bottom. Okay, our natural numbers all the way at the bottom, and then when we moved up into whole numbers, we said it's all of these things and. Okay, so whole numbers are all of these things and notice how it's included in that set. So 1 is a natural number. It's also a whole number. It's also an integer. And because it's in this rational set, it's also rational. And it's real. Okay? So if a number is natural, it's also whole and integer and rational and real. So our natural numbers will fit in all 5 of these sets. Our whole numbers, meaning 0 plus the naturals, will fit in 4 sets. Our integers will fit in 3 sets, and our rational will fit in 2 sets. And see the separation between irrational and rational. You can't ever have both. If it's rational, then it's never going to be irrational. If it's irrational, it's never going to be rational. And some of the examples I want to highlight here. Okay, so under my rational numbers, we see, hey, I've got my fractions. Okay, that makes sense. 0. 0 shows up here again because it's also a whole number. It's also an integer, so it's going to be in rational. All right. We have square root of 9. What's the square root of 9 simplify to? 3. Okay, so I see that that's rational because it equals 3. So square root of 9 is also a natural number because it simplifies to, so it's natural and it's whole and it's an integer because when I simplify it, it's 3. Okay. We also have repeating decimals. Okay, using a little bit of algebra, we can rewrite decimals that repeat and have the same pattern over and over and over as a fraction. So if it repeats, then we have a rational expression. If it's a decimal that terminates, it stops, it ends, I can write it as a fraction, meaning it's rational. So here I have 3 and 57 hundredths. Okay, now I have a fraction. Now I can see that it is a ratio. It is rational. Compare it to our irrational. We have pi, ratio between circumference and diameter. Pi. Okay, e is another irrational number like pi. It's called Euler's number. Okay, very big in logarithms and trigonometry. Square root of 2. What's the square root of 2? Does anyone know what the square root of 2 is? 1 point something, something, something. It never ends and it never repeats. So our square roots of non-perfect squares are irrational. I can get the square root of 9 and get an integer, but I can't do it with the square root of 2. Okay? And again, we see how we have no repeating pattern there. So those are our irrational versus our real number. All of those are real. Okay? And if we wanted non-real, we'd have this little subsection way over here of non-real, and that would just be the square root of -1. And that's it.
So square root of 2 is
correct, because it's irrational. If it's over here at irrational, it is none of those. It can never be any of these if it's irrational. Okay? But if it's over here, it has a possibility to be in multiple of these categories depending on the number. Yes, because it has a repeating pattern, and it's, I think it's like 8/9 if I remember off the top of my head. Okay? We can use a little bit of algebra to rewrite it as a fraction. Okay? Granted, it's been like 6 years since I've done that, so I kind of forgot how to do it. All right, those are our real numbers. All right, and keep that chart handy because it's really useful to kind of go back and look at it from time to time. Absolute value. Absolute value measures distance from 0. Okay, absolute value is always what? Positive. Just think about it. It's measuring a distance, and a distance can't be negative. If I walk 4 feet this way, and then I turn around, and I walk 4 feet back, was that negative 4 feet? No, it's still 4 feet. Distance can't be negative. Absolute value is measuring the distance. Okay? It's measuring the distance between a number and 0. Now we have another thing we'll see, opposites or inverses, and they are different from absolute value. They're similar, but they're different. So we need to make sure that we're clear on what it is that we're looking at. And we have the little bars that indicate absolute value. Whatever you have in here has to simplify to a positive value. Okay? So we have the absolute value of -4 is saying, well, how far is -4 from 0? It is 4 units from 0. The absolute value of 5, how far is 5 from 0? It is 5 units from 0. Okay? And it doesn't matter how complicated or simple the number is. It's a positive, boom, you got the absolute value. But you've got to pay attention to what's inside and outside. Because notice here, you've got negatives outside the absolute value. So I want you to think about what that might do to our number. And we're going to go ahead and do some of that. On your device, I want you to tell me what is the absolute value of 4. How lower from the number line? From 0 on the number line. How far is 4 from 0 on the number line? 7 seconds. Four units from 0. Make it positive. Absolute value of -2/3. How far is -2/3 from 0 on the number line? Okay, 2/3. 2/3 of units. Okay? Take the negative, make it positive. Okay, and we're not going to do any changing of the fraction, we're just going to make it positive. So now here you might want to think a little bit outside the box. If I have negative absolute value of 3.4, if I find the absolute value of 3.4 first, but what is that negative going to do afterwards? What is that negative going to do after I find the absolute value? Find the absolute value first, and then deal with the fact that I have a negative number there. So if I deal with that absolute value first, okay, ignore the fact that I have a negative and just focus on this part. What's the absolute value of 3.4? 3.4, right? So this becomes 3.4. Now that that's dealt with, this comes back down and makes it negative because that negative is on the outside. So it gets applied after I evaluate the absolute value. Okay? So evaluate the absolute value first, and then apply the negative that's left over. Okay? Similar, the negative absolute value of -6. The negative absolute value of -6. Same idea. Deal with your absolute value first. What is the absolute value of -6? 6. And then this negative just comes along for the ride afterwards. Think about evaluating that in the right order of the operations, which of course we'll dig into more tomorrow. I think the rest of what we're doing is going to be some vocab, so I'm going to talk about some of these here. All right. When we looked at our rational numbers, remember our rational numbers were all values of x, all elements of x, such that x could be written as a fraction. I forgot how I wrote it. But we're looking at it has to be written as a fraction where b cannot equal 0. All right? If I can write it as a fraction of integers where b doesn't equal 0, then it's a rational number. And the reason that b can't equal 0 is because we end up getting an undefined value. All right? Now, we have a term called reciprocals, and we use reciprocals for a lot of things. First thing we're going to use it for is dividing real numbers. Okay? Doing division with real numbers, we're going to use reciprocals. The thing with reciprocals is when we multiply the two numbers, we always get a solution of 1. Think of reciprocals as flipping the fraction. Okay? So if I have the number 1/4, It's a rational number. It's a fraction. Okay. What happens when I flip that fraction? What do I get? 4 over 1. And then I can always simplify it to be 4. So 1/4 and 4 are reciprocal values. 1/4 and 4 are reciprocal values, and I can prove it by multiplying them to get 1. Okay, so reciprocals can always be multiplied. All right. The quotient of any real number and 0 is undefined. The quotient of 0 and any real number is going to be 0. So notice the difference between these two. You can't divide by 0, but you can divide 0 by anything. Okay? You can't divide by 0, but you can divide 0 by anything. And you'll see what the answer is. So if we divide by 0, it's always undefined. But if we divide 0 by something, it always equals 0. That's the difference between those two. 2 more slides, I think. I talked about absolute value. We want to differentiate between absolute value and opposites. Okay? So the absolute value of -5, all right, let me do the absolute value of 5 is still 5. Okay? Distance from 0, always positive. Opposites says go to the other side of the number line from 0. Okay? What's the other side? We're going to switch the sign. Okay? So if I want to know what's the opposite of 5, well, what number is the same distance but on the other side? -5. Okay? The opposite of 5 is -5. Okay? Because -5 is the same absolute value, just on the other side. Okay? So the difference between opposite and absolute value, you need to be able to distinguish between the two. Absolute value is always positive. Opposite, also called inverse, we will switch the sign. If it's positive, make it negative. If it's negative, make it positive. Okay? And then the double negative property says that for every real number, if we have a double negative, it ends up being that same base. So if I have a -5, it's just 5. If I have a -1/2, it's just 1/2. The double negative cancels out. Okay? All right? So what's the opposite of 9 going to be? -9. Okay? That's the opposite. I'm going to add in reciprocal as well. What's the reciprocal of 9? That's the opposite. What's the reciprocal? 1 over 9. Okay? What's the opposite of 3/4? The opposite. -3/4. What's the reciprocal of 3/4? 4/3. Okay? What's the opposite of -3.5? 3.5. I'm not going to have you do the reciprocal now, but we will later. Okay? All right?
Opposite is just positive, and whether it's positive or negative.
Opposite is switch the sign. Reciprocal is flip the fraction. Absolute value says make it positive. And this will be our last one. This is just a chart. I'm not going to spend too much time. This is just kind of our phrases that mean math stuff. Okay? This is really important, especially if English isn't your first language, so that when you're reading directions and problems, you can kind of pick up on what it's even asking for. Because a question may say, it won't just say 5 plus 2. It'll say, what is the sum of 5 and 2? And you have to go and look at this. Okay, well, sum means addition, so I need to add those two numbers together. It should be. It's on the subtraction, all these terms, multiplication. You'll see product and quotient a lot. Okay, we use the words product and quotient all the time. Sum and difference for addition, subtraction, those are used the most, but you'll see these all over the place. Ratio, notice ratio. Ratio just means division. Fractions mean division. Okay, so a ratio of 5 and 7 is the fraction 5/7. Divide 5 by 7. Okay, this is nice to just have in case you forget what a term means, so that you can reference it quickly and move on. I find 9 times out of 10, the biggest hang-up is not knowing what it means, and then you're like, oh, okay, now I can do it. All right, especially if English isn't your first language. Questions, comments, concerns? Hopefully a lot of this was familiar, and just kind of refresh and bring it back to the forefront in your mind. You can always ask me questions. Again, I'm here. Study hours, I'm here after school till 4. If you have any questions or long, come see me.